Last time we saw how the resistance of a resistor depends upon its physical attributes. The resistance is related to the length of the resistor, the cross-sectional area of the resistor, and the coefficient of resistivity, which depends on the material that the resistor is made from. Now, this resistivity depends itself upon temperature. Electrons generally have a harder time moving through a resistor when the atoms are moving a lot, and so the resistivity for most materials increases with increasing temperature. So we can calculate the resistivity given the resistivity of a material at a reference temperature, and this reference temperature is T sub 0. And then if we know also the temperature coefficient of resistivity, which can be looked up in a table for various materials, and the new temperature for our material. So we need to know the resistivity of the material at that reference temperature, and then what the new temperature is, and the coefficient of resistivity that varies based on temperature in order to find the new resistivity of the material. This relationship then also works for resistance, since resistance is directly proportional to resistivity. So the new resistance of a material at a new temperature will equal the resistance at a reference temperature, and then we also need to know the temperature coefficient of resistivity. So let's practice using these relationships with an example problem. At 20 degrees Celsius, the carbon resistor in an electric circuit connected to a 5-volt battery has a resistance of 200 ohms. We want to know what is the current in the circuit when the temperature of the carbon rises to 80 degrees Celsius. So since the carbon is increasing in temperature, its resistance is going to change from the value it has at 20 degrees Celsius. So let's first write a picture of this circuit so we can get an idea of how it is working. So this circuit has in it a 5-volt battery, and then it also has a resistor. And the resistance of this resistor is varying. Now, if the temperature is changing, then the resistance will also change. And we know that R is equal to R naught. So the new resistance is equal to the resistance that's known at a certain temperature times 1 plus the temperature coefficient of resistivity for carbon times the new temperature minus the reference temperature at which we know the resistance. So we can plug in numbers to this expression. So originally the resistor has a resistance of 200 ohms, and we multiply that times 1 plus the temperature coefficient of resistivity. So if we look up the temperature coefficient of resistivity for carbon, we'll find that it's equal to negative 0.5 times 10 to the minus third per degrees Celsius. So you can look up temperature coefficients of resistivity in your textbook. You'll notice that carbon is a very odd material. It actually has a resistance that goes down a little bit as its temperature increases. So then we multiply this temperature coefficient of resistivity times the temperature difference, the new temperature, which is 80 degrees Celsius, minus the temperature at which we know the resistance, which is 20 degrees Celsius. And you notice I'm using Celsius. This is a temperature difference, so it's okay to use Celsius as well as Kelvin. We'll get the same answer. So this gives us a new resistance at 80 degrees of 194 ohms. So the final step, now that we know the new resistance of our resistor, is to figure out what is the current. And we can do that using Ohm's law. So the potential difference across our resistor is equal to the current through the resistor times the resistance. So if we want to find current, current is going to be the potential difference across the resistor divided by the resistance. So since the resistor is hooked up to a 5-volt battery, we know the 5-volt battery is going to raise the potential by 5 volts, and so that potential will need to be lost across that resistor. So the potential difference across the resistor is 5 volts, and then we divide by the value of the resistance, 194 ohms. So that is going to give us a current then of 0.026 amps, or we could also write that as 26 milliamps. And that will be the current through the circuit and through the resistor. Now, there are some special materials where the resistance actually drops all the way to 0 below a critical temperature. So below this temperature, the material does not have any resistance at all, and the resistance just goes to 0. If you were to put a current through this type of material, it would just pretty much go forever. You wouldn't even have to hook it up to a battery to keep the current going because there is no resistance. So you can see in this table, there are a list of some materials and what this critical temperature is. And you can see the critical temperature is pretty cold. These critical temperatures are often very close to absolute 0. And so superconductors can be difficult to achieve for this reason, because you have to cool them down so much. Now, there are also materials which are known as high temperature superconductors, meaning they have a critical temperature which is maybe above 100 degrees Kelvin. This is still really, really, really cold, but the temperatures here are easier to achieve. So some high temperature superconductors can be brought below their critical temperature with something like liquid nitrogen. So still pretty cold, but quite a bit more achievable. Now, superconductors could be very useful in creating magnets. There are already superconducting magnets in use, and these are typically research magnets, magnets for MRI machines, and also used in particle colliders. And these superconducting magnets produce the very highest magnetic fields because since the current can flow in them and create the magnetic field, and the current can flow without resistance, you can have a very strong current and there's no resistance, and so these magnets won't overheat. And so superconductors can be very useful materials. Next, you'll watch a video showing some of the nifty things you can do with superconductors.